This is our lecture portion, our first lecture portion today, where I'll spend some time talking about the water in the air and what characteristics that gives the air, how we measure it, that sort of thing. And then we'll go on to our lab where we'll actually measure the amount of water in the air in the room today. Just to sort of bring jog your memory back to what I promised we'd be talking about in this unit. This is a map of relative humidity in the United States on whatever day it was taken. What I've written here on my website says dew, frost, fog, clouds, rain, and every other kind of precipitation imaginable are caused by water molecules in the air. The amount of water molecules is commonly known as humidity and helps drive local and global weather patterns. How do we measure humidity and how does it affect clouds precipitation? So we're going to hit on that first topic today. How are we going to measure humidity? But first, I think I'll start with what happens to water when it's exposed to different temperatures, just sort of a review. And gentlemen, you close the lines, please. Okay, so humidity. Right. So where I'm going to start today is just the phase changes of water. What happens when you heat it up, what happens when you cool it down. And as you know, the coldest phase of matter is solid. The middle phase would be liquid. Sure. And the warmest phase would be gas. In general, when you take heat away, the molecules pack together and you go in that direction. When you add heat to it, it spreads the molecules apart and you go in this direction. There's a couple of notable exceptions to that, like for example when water goes from liquid to solid it gets bigger. But in general, if you take heat away you're going to go in that direction, and you're going to add heat to it you're going to go in this direction because you're spreading the molecules out this way and you're condensing the molecules together if you go that way. Okay, what do we call these phase changes? Solid to liquid.
Start young.
Alright, when something goes from solid to liquid, that's a phase change. We have a name for it. When something goes from solid to liquid, what do we call that?
Melting.
Melting. Yeah. And then when it goes from a liquid into a gas?
Boiling point.
Boiling or evaporating. Yeah, I'm going to go with evaporation on this one. Okay, gas back to liquid.
Condensation.
Condensation.
Are you kidding me? How did you know that?
You've probably heard of condensation, right?
I've heard it before, but I didn't guess it.
Alright, well next time you get out of the shower in the morning, look at the mirror and go, condensation!
Okay.
And liquid to solid. Freezing. Okay, there are two more of these that we don't use as commonly, but they do happen, and you've probably observed them once or twice. It's possible for something to go straight from solid phase to gas phase. Dry ice does it. If you have dry ice, which is solid carbon dioxide, it goes straight to gas without turning into a liquid. Iodine crystals will do this. This is called sublimation.
What if it goes straight from a gas to a solid?
I can do that too. Water does that. Water goes straight from gas phase to solid phase in the winter time when we get frost. Actually, it's usually more like in the fall or the spring. That's called deposition.
What if it goes straight from a liquid to a gas?
So we call that evaporation. Yeah, there's a fourth state of matter called plasma, but we're not going to worry about that one. Okay, so humidity is most simply defined as water in the air. And what that means is that some number of air molecules, you may remember from back the very first day of this unit, I said that we don't classify water molecules as part of that 100% because they're usually liquid. However, if we were to examine all the air molecules in this room, we'd find that somewhere between about a fraction of 1% up to maybe about 5% are actually water molecules. So Humidity is the measurement of how many of these molecules in an air mass are actually water. There's two ways to measure it. One's called specific humidity and one is called relative humidity. I'm going to briefly talk about specific humidity. We don't use it as much as relative humidity. And then we'll spend more time talking about relative humidity because it's what we use commonly and we're going to test it in the lab today. So specific humidity that actually tells you the weight or the mass of water in the air. How would we measure it? Well, I could say, for example, the specific humidity of the air today is 1 gram per kilogram. And what that would mean was, in 1 kilogram of air, 1 gram of it would be water. So this is the, I'll say, a measurement of the mass of water in the air. The measurement of the mass of the water in the air, and it's measured in grams of water per kilogram of air. Okay, specific humidity, that's the measurement of the mass of water in the air, measured in grams of water per kilogram of air. But this is not as useful to us as what's called relative humidity. So I'm going to move on to that one. And I'm going to move over here so I'll have more room. And the first thing to understand, in order to understand relative humidity, you have to understand capacity. Anybody know what the word capacity means? How much it can hold, says Brian, he's right. What kind of things have you heard of the capacity of? Of an elevator, sure. Capacity of like 2,000 pounds maybe? What's that? A boat is in weight or passengers or something like that. A stadium. The TD Bank North Garden has a capacity of about 20,000 people, something like that. An air mass has a capacity for water. It can hold so many water molecules. It's dependent upon the temperature, and we'll get more into that next class, but suffice for this point to know that every air mass has a capacity to water, or excuse me, for water. It can only hold so much. So, an air mass has a capacity for water. And the maximum capacity could possibly be is like 5%, but usually it's less than that. Like 5% of the molecules could be. But I'm going to stop talking about percentages because it will just get confusing because relative humidity is also a percentage. So an air mass has a capacity for water. When we measure relative humidity, we're basically saying what percentage of that capacity is being filled right now. Like if an air mass has some capacity for water, if the relative humidity is 50%, it means that the air is holding at 50% of its max capacity. So, relative humidity tells us what percentage of an air mass's capacity for water is currently filled. It's not really important that we know what the capacity is because it changes. It's only important that we know what percentage of that capacity is filled with water right now. Let's go ahead and look at the weather.com, and we'll see what the relative humidity in South Portland is right now. So right now it says humidity 46%. What that's telling us is the mass of air outside today has some capacity for water, and that capacity is filled up to about 46% right now. 46% of that capacity is being filled. What this does not mean, and this is the number one mistake people usually make, 46% relative humidity does not mean that 46% of the air molecules in here are actually water molecules, because we'd be dead. It means that 46% of the capacity for water is being filled. So probably if we wanted to know what percentage of these air molecules in here were water, it's probably still only about 1 or 2%. But 1 or 2% is 46% of the total capacity that this air mass is able to hold today. That's what relative humidity means. We can measure it using something called a psychrometer. And it's actually just a fancy way of saying a wet bulb, dry bulb thermometer. And so I think we're ready. Let me check real quick, but I believe we are ready to go on and do our lab experiment. There is one more thing I want to tell you. Okay. Basically this. When the relative humidity reaches 100%, it means the air can't hold any more water. It's at full capacity. And when that happens, it doesn't mean you can't force more water to evaporate. You can. If it's 100% relative humidity, you can still put a pot of water on the stove and have it boil. But when your air is at 100% relative humidity, every molecule of water that evaporates means a molecule of water is going to condense somewhere else. Okay? So if you force more water into the air when it's at 100% relative humidity, you're going to be forcing water to condense somewhere else. So you're going to get droplets of liquid water forming somewhere else in that general area when you're evaporating more water. Like when you get into the shower in the morning and you blast the hot water, your air mass in the bathroom is going up to 100%, and at that moment when it hits 100% and more water is still evaporating, you're going to get condensation all over everything. That's what's happening. So, last thing here to write would be when relative humidity reaches 100%, every molecule that evaporates means a molecule condenses somewhere else.
Is that your daughter when she was like really young?
Less than a year, yeah. They vary. Actually, some of them are very recent. Okay, so when relative humidity reaches 100%, every molecule that evaporates means a molecule condenses somewhere else in the air mass. And now we're ready to move on to today's laboratory experiment. I'm going to refer back to these two statements. The one that says, if air is humid, it is difficult to get more water to evaporate. If air is dry, it is easy to get more water to evaporate. What you observed today is called evaporative cooling. Today, as you saw the relative humidity, we looked at the web page, it said the relative humidity was in the 40% range. That's pretty low. Last week when I had classes do this on Friday, it was more of like in the 80 or 90% range. So that means that today it was a lot easier to get water to evaporate than it was for them. Okay? Now, here is the strange thing that happened. Although you may not have thought of it this way. You just took room temperature water and you fanned it with room temperature air and the water got colder. Why would water have gotten colder if you were blowing room temperature air across it? The air was the same temperature as the water. Why would fanning the water with air that's the same temperature as the water make the water get colder? Or, by the same token, we could have even have done it with warmer air. We could have taken air that was warmer than the water and fanned the water and still gotten the water to cool off. Why? That's the question. Yes?
Is this something to do with the wind chill factor?
Yes, the wind chill factor works the same way. If there's wind, if it's windy, it will have an effect of making it feel colder. The explanation is going to require me to go back and remind you of what temperature is. Or you can remind me, what is temperature? I said, what's the temperature of water when you put a temp probe in water? What's it actually telling you about the molecules? Yes, Dave? How fast they're moving. Specifically, the average speed or the average energy. So let me write that again. Temp is the average energy or average speed of the molecules. For our purposes, we'll assume those do the same thing right now. So temperature is the average speed it's actually more accurate to say the average kinetic energy, but we don't need to worry about that until you get to physics. So temperature is the average speed or kinetic energy of the molecules. So if you got a temp probe sticking into a tub of water, or a wet paper towel in the case of this lab, what it's actually measuring is the average speed of all the water molecules. The reason I underlined the word average is because they're not all the same. Some of the molecules are moving much faster than others. In fact, some of them have so much energy, they're almost ready to evaporate right now. And then some of them are moving very slowly. They don't have nearly enough energy to evaporate. That's also important. So, some molecules have almost enough energy to evaporate. So when you go ahead and you start fanning, if I get my glass of water here and I start fanning it, the movement of the air molecules is able to give those water molecules just a little bit more energy. And the ones that have almost enough energy to evaporate are going to go, and they're going to go evaporate up into the air. Now, tell me something. Let's say we took the class average on an exam. Like the last exam was out of 20 points. Let's say the class average was 15 out of 20. And I took the 5 people with the highest scores and I said, okay, go out in the hallway. And then we averaged the scores of the remaining people in the class. What would happen to the average? The average would go down. If you take the highest scorers out of the class, the average is going to go down. What do you think is going to happen to the average energy of the molecules if you take out the hottest ones? For the same reason, it's going to go down. So here's what's happening. Some of the molecules have almost enough energy to evaporate. You're giving the water a little more energy. The hottest molecules will evaporate, which will make the average energy of the molecules go down. And that's what the temperature is, the average. So you can drive the temperature down by giving the water just enough energy to evaporate the warmest molecules. That's what you're doing. That's what's called evaporative cooling. So, say when the hottest molecules, I use this word hottest in the quotes here, when the hottest molecules gain enough energy to evaporate, when the hottest molecules gain enough energy to evaporate, the average energy of the remaining molecules goes down. why fanning your wet temp probe made it go down in temperature. Because you were giving the hottest molecules in that paper towel just enough energy to evaporate. And that was in turn driving the average of the remaining molecules down. So the temperature went down, 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 to the point where you got the water to sometimes 7 or 8 degrees colder than the air you were fanning it with. By the way, this is why sweat works. The idea of sweat doesn't make very much sense, does it? You think sweat is supposed to cool you off, but when you sweat, the water that comes out of your skin is the same temperature as your body temperature, so why would that make you any cooler? The answer is it wouldn't. Sweat wouldn't make you any cooler unless there's a little bit of motion of the air, or there's a little breeze, and then some of the sweat molecules, the hottest water molecules in that sweat would evaporate, and then all of a sudden the sweat would be a lower temperature than your body temperature, and then it would cool you off. That's how it works. Yes, you need sweat, but then you also need some extra energy, be it like you moving through the air or the air moving across you, to evaporate some of those molecules in your sweat and make the remaining ones go down in temperature. That's also why it feels cold when you step out of a 75-degree pool into 95-degree weather. You think, hey, I should feel warmer. I'm getting out of cold water into warmer air. But what happens, you step out of the water and you still have some of that water on you, and the warm breeze evaporates the warmest molecules and makes the water on you cool off. That's why it feels actually warmer sometimes when you stay in the water, even though the air is warmer than the water.